Okay, so yesterday we were discussing about the one important parameter, which is the drift mobility, and normally it is defined by drift mobility is or drift velocity. Rather, we defined the drift velocity as the drift mobility into electric field. So when you apply an electric field, so the electrons will have a drift velocity. So before, when you don't have an electric field, so the electrons, they undergo random uh, motion, and the velocity, when you measure the average velocity of the electrons, these conduction electrons, so the average velocity will be 0. However, when you apply an electric field, so there will be a net displacement of the electron in opposite to the applied field direction, and that is what is known as drift. And due to that, so you will have an electric current. Now this drift mobility, so you can also calculate the conductivity if you know the drift mobility, so which is given by this relation. So sigma is your conductivity and n is your number of electrons per unit volume, and E is the charge, of course, and mu d is your drift mobility. So if you know these, so here what we see is a correspondence between a macroscopic quantity which we can measure, the conductivity in this case, so which we can measure by applying a current and or applying a voltage and measuring the current, or vice versa. And if we know the dimension of the material, so we can calculate what is the conductivity or resistivity of the material. And this is related to all the microscopic parameter of so the electron charge, number of electrons, and the drift mobility, which are all depend on the or so that how electron responds to an electric field. So this quantity, this drift mobility, is quite useful for most of the electronic devices. So when we want to compare the performance of electronic devices, normally we talk about what is the mobility of the charge carrier in that device. And as I said, so what is required or what we want for electronic devices, it should, I mean, whatever task it performs. So if it is doing some arithmetic operation or logic operation or any operation, it should do it as fast as possible. So that, yeah, basically we, so even if let's say it communicates with the memory, so it should happen faster, or if it is performing any operation, so it should be faster that that we get the result or output as quickly as possible. And this is only possible if the mobility is high. Now, one thing you look, you should be careful about that the conductivity depends on all these three parameters, so N, E, and mu D. And even if let's say the mobility is high, that doesn't mean conductivity will be always high. So for a metal, so you need, or for any material, if you want the conductivity should be high, so you need both N should be high and mu D should be high. So then only your sigma will be high. Otherwise, it may happen your mobility of the charge carrier is high, but the number of charge carriers, so N, is small, and in that case, your conductivity will not be that high. Okay, so you will see one example here, and then these things will be clear. So remember, so you have to be careful that if the drift mobility is high, that doesn't mean conductivity will always be high, because in most semiconductors, so actually this mu d, your drift mobility is high. However, n is small, and that's why your conductivity is small in semiconductors. So let's solve one example. So this is so whatever I'm covering right now is from the book eso kasab, which I shared earlier in the first class. And so this is an example we will do, and we can, so what the problem is that we calculate the drift mobility. So calculate the drift mobility and the mean scattering time of conduction electrons in copper at room temperature. So we want to calculate the drift mobility and tau, that is the mean scattering time of copper at room temperature, and what is given is the conductivity is given. So conductivity is, so we have copper, and the conductivity is 5.9 into 10 to the power 5 ohm inverse centimeter inverse. So we have the density D, which is 8.96 gram per centimeter cube, and the atomic mass is 63.5 gram per mole. So we have to first calculate the drift mobility and the scattering time, or the relaxation time. So to calculate, now if you use the relation N E into mu D, so we need to calculate what is mu D. That is what we need to calculate. So mu D is equal to sigma by NE. Now you have to calculate N. What is N? We don't know yet, so that we need to calculate. Now, let's say if you look at copper, so copper, the electronic configuration of copper, so it is 4s, or rather, I should say 3d10. So argon 3d10 and 4s1. So copper is 29, and the electronic configuration is like this. So you have one s electron, which is the valence electron, which most likely, so we can assume that this copper conductivity is due to this valence electron, which is coming from this 4s valence electron. So that contributes to the conductivity. And that means we can assume that each copper atom, so each copper atom contributes one electron, which is the 4s electron, the valence electron, and this electron is responsible for the conductivity. So now, if we want to calculate what is N, N is, that is nothing but the number of conduction electrons per unit volume. So we can say, if we know the number of atoms per unit volume, and we say each atom is contributing one electron, so we can calculate what is, or we can know what is N. So then how do we calculate the number of atoms per unit volume? The number of atoms per unit volume. So this is given by this expression. You already know about this. So this is DNA by M atomic mass. So D is the density, N is the Avogadro's number, and this is the atomic mass. So if you substitute all these, which are given here, so Na is 6.02 into 10 to the power 23. So number of atoms per unit volume will be, so if you substitute all the numbers, so you will get a value of about 8.5 into 10 to the power 22 atoms for volume. Or rather, normally, since it is in centimeter, so we will write it number of atoms per into centimeter minus 3. So this is the total number of atoms, and how many electrons, conduction electrons will be there? Number of conduction electrons will be, assuming that each atom contributes 1 electron, so that will be again the same 8.5 into 10 to the power 22 electrons centimeter. So now we can calculate mu d, what is the drift mobility. We can calculate that. So you substitute all the parameters. So sigma is 5.9 into 10 to the power 5 mega inverse centimeter inverse. So always be careful about the units. Sometimes sigma can be given in omega inverse, meter inverse. So you have to be careful when you solve these equations. And then we substitute 8.5 into 10 to the 22 centimeter minus cube into the electronic charge, which is 1.6 10 to the minus 19 coulomb. So now if you simplify or solve this, so what you will get a value is 43.4 centimeter square volt inverse second inverse. So this is the unit of mobility. So this is 43.4 centimeter square V voltage inverse and second inverse. So you can also write it something like 43.4 into 10 to the power minus 4 meter square volt inverse second inverse. So this is the drift mobility in copper. We also wanted to calculate, so let's go back to the problem. So we want to calculate the drift mobility, and we want to calculate the relaxation time tau. So what is relaxation time tau? How it is related to the drift mobility? So when we saw the definition of drift mobility, it is given by E tau by ME. This is the definition of the drift mobility, because we said, so this comes from the relation VD is mu d E, and when we did the relation, it is something like this. Okay, E tau by ME into E. So this is, from this relation we got this definition of drift mobility. So this is mu d is, so we have to calculate tau. Since we know all the other parameters, so we can calculate tau, which will be ME into mu d by E. Now ME, so the mass of the electron is 9.1 into 10 to the minus 31 kilogram. So here we will be using the SI unit instead of the CDS unit that we used earlier. So mu d, I write 43.4 into 10 to the power minus 4 meter square volt inverse second inverse into 9.1 10 to the power minus 31. So you can also express it in gram and then do the calculation as well. So again 1.6 into 10 to the minus 19 coulomb, which after simplifying, so you will get a number which is equal to uh, 2.5 into 10 to the power minus 14 seconds. So you can see this relaxation time is really small. Okay, so the scattering is quite high, but it is still fine in terms of getting a reasonable conductivity. So this tau time between two collision is of the order of 10 to the power minus 14 seconds. Okay, so you can imagine how fast the scattering is happening, and still you get a conductivity, good conductivity in this material. So also I think there was one more thing we need to calculate. So we wanted to calculate the mobility, then the scattering time, and then yeah, if the mean speed of the conduction electron is, so the mean speed is this much, and what is the mean free path between collision. Uh, so we know the time, that is a relaxation time or time taken between two collision is this much, and the mean speed is of electron is given by 1.6 into 10 to the power 6 meter per second. So this is the electrons are moving this with this velocity, or the average speed of the electron due to the thermal motion. This is at room temperature. Okay. Roughly, most of most of these electrons will have this. This will be the mean speed of the electrons or the charge carriers in the metallic systems. And what is we need to calculate the mean free path. So what is mean free path? So which is normally given by let's say we call it L, which will be U, the speed into time. That is the mean free path. So that means this is so if the electron has a speed of U, and it travels without getting scattered for a time tau, so how far it will move before it gets scattered. So what is the distance it will travel before it gets scattered? That is what the mean free path means. Okay. So it is nothing but the multiplication of these two. So if you just multiply that, so you will get a number something like 39 nanometer. So which is 39 into 10 to the power minus 9
Sir,
meter. Yes,
sir, here u is the speed just after collision,
just after collision. Yes.
and this mean free path
This
L
is
is a
not drift. This is not drift
no.
velocity.
This is not drift velocity, right? So, sir, my doubt here was why. So during like our electron has just collided, and its initial velocity just after collision is 1.6 into 10 to power 6, and we have also applied an electric field.
Yes.
So, so why are we not considering the like acceleration of the electron due to the electric field? Like
No,
I
if you look at so if you want to add here, so you are saying, so we can add, there will
plus
be
half it.
extra velocity term here or
Yes,
speed
yes,
term
yes,
here, right?
yes,
So
sir.
actually the due to drift, but due to
Yes,
drift, so if you calculate the drift, the speed due to drift, let's say the magnitude, if is V, or you let's say U D, is typically of the order of minus 10 to the minus 2 or to 10 to the minus 1 meter per second. Okay. So, which is really the contribution is, compared to this mean speed of the electron, due to the temperature, it is really negligible. So it is still will be the dominating term here, okay, in terms of the magnitude. Okay, so the mean speed is always much higher compared to the drift speed. So you can add, but then this number will not change. So it will be maybe one order of magnitude more or like that. So there
Okay.
is not a big difference in that. So it will be, so the point what I want to emphasize is that the electron will travel probably a few hundred nanometer in the material. So your material will be typically in millimeter or maybe in centimeter size. Okay, so which is of the order of 10 to the power minus 2 meters, okay, or minus 3 meters. However, the electron will travel only a few hundred nanometer, and then it will get scattered. Okay, so that is what uh, the point here I wanted to emphasize, that mean free path, these are very small. Okay, so electron gets scattered. So the scattering can happen due to lattice vibration or anything, but it scatters really very fast, as well as it doesn't travel a far distance as well. Okay, so even if you add this extra term here, so it will not change this value. Change in the sense like the order that what I am talking about. So only the drift or this electric field will make sure that electrons they move in the direction of applied field. Okay, so they will not determine the speed of the electron actually. So the speed is again determined by the temperature that you are. What is the temperature, and what is what is the temperature at that like when you are doing the or when you are applying the electric field or the voltage. Okay, is it clear? Yeah, so this mean the speed is different from the drift speed. Okay. Okay, so now I think one additional thing maybe you can read about, so which you have already performed the experiments, this Hall effect you have all done in your physics lab. So maybe you can correlate these concepts with the Hall effect as well. So in Hall effect, so you can read it about it and understand this Hall effect, where you also use a term known as mobility or a Hall mobility, and how it is different from this drift mobility. So you can read about that. So the mobility due to this drift and the mobility that you see in when you do a Hall measurement, so are they similar or different? So you can read about it. Okay. Yeah, so another interesting thing, so this is about the metallic system. So if I take a silicon, let's say, so which is a semiconductor, so the drift mobility of electron is given by 1350 centimeter square volt inverse second inverse. And you see the mobility of electron in silicon is much higher compared to copper. However, the value of the number of charge carrier n is order of 10 to the power 10 centimeter cube. So this is 10 to the power 10 electrons per centimeter cube. You have other 10 to the power 10 electrons per unit volume you have in silicon, the charge carrier. And that's why sigma of silicon is much smaller than sigma of copper. Although the mu, the drift mobility of silicon is much higher than drift mobility of copper. But since the number n, the number density is really small in silicon, so that's why you have a small conductivity of silicon. So, but if you look at silicon, the configuration, electronic configuration, so you have, so 14, so 1s2, 2s2, 2p6, 3s2, and 3p2, right? This is the electronic configuration of silicon. And if you say the p orbital will contribute to the valence electron, so they are the valence electron, so they will, and you say, okay, I should have 2 electrons from each silicon which will participate in the conductivity. However, that is not the case. What we see is this number density is much smaller. So why is that the case? In order to understand that, so we need to, so one thing, what is different between a piece of copper and a piece of silicon? The difference is, of course, what is the nature of the bonding, okay? So if you take a silicon, like a solid silicon, so the bonding is mostly between the silicon and silicon atoms. It will be a covalent bonding, and the conductivity or this number density is different due to something known as the energy bands that form in materials. So we will try to understand so not really going into the mathematics so much, so we will try to understand qualitatively how these energy bands are formed and how they are responsible for different number density and the conductivity, or how they play a role in conductivity of materials. And in order to understand that, so a little bit of quantum mechanics is required, and I think you already have a bit of introduction to quantum mechanics in the last semester. So let me quickly jump to this question. So we will start with a very basic system, what you know already. So how a hydrogen molecule is formed. So you also probably know it from chemistry as well. So a hydrogen molecule is nothing but it's like two atoms of hydrogen. So it's a H and H put together. So you make the hydrogen molecule. And we will use the concepts from quantum mechanics to see how this hydrogen molecule or white forms. So hydrogen is like so 1s1, right? So 1 electron. So it has 1s orbital, which is known as a symmetric orbital. And when they are far away, like the picture shown here, okay, so when they are far away from each other, so they are like isolated atoms. So we say the distance, so one atom A, another hydrogen atom B, and the separation is like infinite. So they will be behaving like individual atoms. And this wave function that represents the electron, the quantum mechanical particle here, that is described by a wave function psi 1s. Okay, so since it is a 1s orbital, electron in the 1s orbital, So the wave function we represent by psi 1s. So similarly, since it is associated with A, so we said psi 1s are A, and it will be symmetric, spherically symmetric. So the wave function is represented like this, the quantum mechanical wave function. And now we bring them closer, so they will start to feel each other, or that means there will be some interaction that will happen. And what will that lead to? So that when these interactions happen, so you will have a formation of, instead of atomic orbitals, so you will have the formation of molecular orbitals. So if you don't understand anything in here in this picture, so let me know. So what you have is you have two atomic orbitals. So that means you have electron in the first electron and the positive ion, or the proton, as well as electron and the proton in the both the atomic both the atoms. However, when you bring them together closer, so you have a overlap of these electrons orbitals. Okay, so this 1s orbital will overlap, and that will lead to a formation of these molecular orbitals. So one molecular orbital is known as the bonding molecular orbital, and the wave function is defined by this. So it is just a sum of the atomic, the wave function 1s orbitals, and the other is the anti-bonding, the molecular orbital. So what is happening is, so you have two electrons as well as two protons. So the electron 1, so this electron, let's say this electron 1 or EA will be also, when you bring them closer, so EA will also, it is interacting with this proton, as well as it will also interact with this proton. So similarly, it will also feel the repulsion from the second electron as well. So similarly, the electron associated with B, that will also interact with the nucleus here, and as well as with the electron here. And so you will have extra electrostatic interaction between these electrons, and due to that, so you will have the formation of these two different orbitals. So instead of having individual atomic orbitals, you will have two molecular orbitals, and the wave function will be basically, one will be the sum of the atomic orbitals, and the other is the difference of the atomic orbitals. And what is the probability distribution? So the probability distribution is nothing but, so the probability distribution, normally if you have a wave function, so it is the modulus square of that wave function, that is your probability distribution. And what it says, that what is the probability of finding the electron in space. Okay, so what is the probability? Then if we see that, so for the molecular orbital, the bonding molecular orbital, so you just take the modulus square of the wave function. So you will see the most likely, the highest probability is still when the electron, like in case of the atomic case, but you still have some probability that electron you can find also in between two atoms. And that is what basically you have the sharing of the electron that is happening, and that is the reason for the bonding of the hydrogen and hydrogen atom. So you have also a probability that you will find the electron in between the two nuclei or two protons. In case of the antibonding orbital, in the right picture here. So you have the probability, again, the distribution is different, but you have a node actually, or you have a zero probability to find them at the uh, center. So that means there is no probability of being the electron being shared between two atoms. Okay. So, so this is about their wave function and their probability distribution. So what about the energy? So what happens to the energy state? So when we started with individual atoms, so the electron energy will be represented by this E1s energy, which normally you would say like something like from the zero level, zero energy level. So the energy will be minus 13.6 eV, right? So this is for the binding of, this is the energy for the electron to, to be bounded with the proton. So this is this much energy, so you need to give so that you can free the electron from or ionize the hydrogen atom. Now, what happens to the energy in this case? So if you have two atoms and now you said you bring them closer and you have a formation of a molecular orbital or two molecular orbitals. Uh, so sometimes you also in chemistry you might have seen that like sigma and sigma star that forms. So basically that is what we will have here. Okay. So again, if you see the picture here, so you have the molecule where, so you have two distinct atoms, so represented by E1s, each has one electron. Now when you bring them closer, so you have this molecular orbital, two molecular orbitals, and the energies are given by E sigma and E sigma star, or the bonding and the anti-bonding energies will be there. And you can clearly see this energy of the bonding molecular orbital is lower compared to the individual atomic, the energy of the electron when they are in the isolated case. And since each state can have two electrons actually, so spin up and spin down, uh, because of your Pauli's exclusion principle, so you have two electrons here in the bonding orbital. And therefore, when you put these hydrogen atoms together and make a molecule, the energy is lower compared to the individual atoms. And that's why it is favorable, or there is a possibility that you have a hydrogen molecule. Otherwise, it will not form. So if you take so if you take helium, for example, so if you see the same case for helium, okay, so let's say you have a helium atom. So again, you have both up and down, and then you bring them together and you have two molecular orbitals. So now when you fill it up with electrons, so you also have your antibonding orbital will also be occupied. Okay, so this is your E. So this is for what I am doing is for helium. So 1s2. So this is E1s, this is E1s, this is E sigma, this is E sigma star. And since the antibonding orbital is also full, so it is not a favorable condition for the helium molecule to form. So therefore you will not have a helium molecule. Now this is a schematic representation what we have. But we want to see what actually happens when we vary the distance between the atoms. So how the energy varies. So how the energy varies as a function of R. R is the separation between atoms. So how this picture looks like. So the picture what we have shown here is like when the condition is favorable for molecule to form. So that means you have an equilibrium separation between the atoms, okay, and that leads to this formation of this molecular orbital, and you have a molecule that has formed in case of hydrogen. But how this E, the energy of the 2H system, hydrogen, when we take two H atoms, and then let's say in the first case they are at infinity, and then we are bringing them slowly. So how the energy varies? So let's look at that. So this is actually the picture how a system of two H atoms, when the energy will vary as a function of R. So here what we have plotted is in the x-axis is the distance or the atomic separation, let's say interatomic separation, and in the y-axis we have the energy. So we said when R is equal to infinite, so both will have the same energy, which is given by E1s. And now when we bring them closer, so we will have a formation of this molecular and two molecular orbitals with different energies. And as we see, go on bringing them closer and closer, so we will see a uh, clearly like at certain separation. So you will have these two energy levels that will appear, and then slowly as you can go bring them closer, so what happened, so you have energy which has a feature like this, okay, and this is your molecular orbital, molecular orbital, energy of one molecular orbital. So we say this is psi sigma, which sometimes also known as a symmetric uh, uh, molecular orbital, and then one is the psi sigma star, okay, the which represents the other molecular orbital with energy E sigma star. This is the energy. And so clearly what you see is, so at a particular separation A, so when R is equal to A, so you have the favorable condition for the molecule to form. So the H2 molecule will form. And the reason here is the energy is the energy in the bonding the molecular orbital is the lowest here, and some you have to give a certain energy if you want to dissociate the molecule, and this energy is typically of the order of 4 point. So this EA or the bonding energy. So the bonding energy bonding, let's say, is 4.52 electron volt, and this A in case of hydrogen molecule is about 0.074 nanometer. Okay, so when this condition is when the atoms are at a distance of 0.074 nanometer, you will have a energy of the bonding molecular orbital which will be lowered from the atomic orbital, or the energy of the atomic orbital, by 4.52 electron volt, and then you have a stable hydrogen molecule will form. So uh, so this is now one thing which you can see here, this in the bonding molecular orbital. So the energy is like as a proportional something like, so we don't know what is like, at least it is inversely proportional to the separation distance, uh, the separation between them, this energy. Or the energy difference. What I'm saying is not energy, but energy. difference, delta E, more or less. But then, so what I mean is this, what is delta E here? So this delta E is nothing but the separation between the energy of the anti-bonding molecular orbital and the bonding molecular orbital. So this delta E. However, if you want to bring the hydrogen atom much closer beyond this equilibrium separation A, so again the situation is different and the energy will again increase because the repulsion will be too high. So there is a equilibrium separation where the electron repulsion as well as the proton repulsion is overcome by the Coulombic attraction of one electron with the second proton, and the second electron with the first proton. Okay, so this is the equilibrium separation condition when you will have the formation of the molecule. Okay, is it clear or any question here? Okay, so now we can extend it to, yes, so we will follow it. So if we take now 3 atoms, so let's say we take 3 hydrogen atoms, so you will have 3 molecular orbitals. Okay, so you will have 3 molecular orbitals. Sorry. And the energies will again vary. So so this energy one can calculate using by solving the Schrodinger's equation. So in quantum mechanics, so when you want to find out the energy state of electron, so basically you solve the Schrodinger equation. So you can solve the Schrodinger equation for hydrogen atom, then hydrogen molecule, and so on, and then you can calculate or find out what is the this energy eigenstates. And here what we are doing is looking at a qualitative explanation or understanding of that. So again, now if you bring 3 atoms, so you'll have 3 molecular orbitals. However, what happens is, again, you have a molecular orbital which is symmetric, where you will have 2 electrons here. That is the minimum energy you will have. Again, at certain equilibrium separation between the atoms. But since you have the third, so you have here H and H system. So since you have a third hydrogen atom where you have another electron, so this electron will go to the second available energy state, and that is a little bit higher compared to the this E1s state. So therefore, you cannot have a H3 molecule, so to say. Okay, so you have a H2 molecule, and rather they would try to have H2 molecule and then maybe another H atom, but you will not have a system with H3 molecule, because since you have another extra electron, which will go to a higher energy level, and therefore the total energy will be much higher compared to when they are in an isolated state. So so now we can go on doing this. Now let's say we will look at such n atoms, but I will not take hydrogen here. So I will take a real metal, which is nothing but lithium. So let's look at lithium. So it is again 1s2, 2s1. So in terms of electronic configuration, so it is very similar to hydrogen, because the 1s orbital is occupied by only 1 electron. So you have 1s orbital which is full, and the 2s orbital has only one electron. So this is actually a lithium is a. So if you take a lithium solid, it is metal. It's a metal. So this, when you take n lithium atoms, so what you will have is formation of n molecular orbitals. Okay. So your energy levels will similarly, so each orbital will have its energy eigenstate. So so you will have n energy states. Uh, and which orbital is most likely to get these n different molecular orbitals? It is the orbital which is actually overlapping. So in this case, in lithium, so the outermost orbital will overlap. So the overlap will happen for the 2s orbital. So will overlap. Okay. And you will have, so similarly then you have this separation. So let's see if I have a picture here. Yeah. Okay, so this is what will happen if you take n atoms, lithium atoms. So you have the 1s level, which is they are not overlapping, and therefore we can say that so, in which case, what do you mean by anti-binding orbitals? Anti-binding, in case of hydrogen atom, 3 hydrogen atom, is that your question? Or here? Oh, okay. I mean, when we talk about a solid, we don't say or give that name as bonding and anti-bonding. So it is not binding, but it is bonding. Okay, so it is a bonding orbital, bonding and anti-bonding. But we don't say here so in case of the solid, we don't say it is a bonding or anti-bonding orbital, because we have n I mean each there will be n energy states, and each state will be associated with some wave function. Okay, and here we are designating is with a wave function psi 1. So we call psi 1 up to psi n. Okay, and what it will be again some linear combination of the atomic orbitals in terms of wave function. So psi 1 will be a linear combination. So combination of the atomic orbitals, let's say A to, I don't know, or I would say let me say it in another way. So we can say here, this is a linear combination of phi 1 to phi n. Okay, and what is phi I? Is it atomic orbital of uh, electron in ith atom. So this electron is nothing but the 2s electron, because there is one electron. So this is the phi I is the represents the wave function. This is the wave function for the 2s electron in ith atom, and your psi 1. So you will have a molecular orbital due to a linear combination of phi 1 to phi n. So this is your wave function of ith uh, uh, so represents. So now what we are saying is electron doesn't belong to any atom, particular atom. So rather it belongs to the solid. Okay, and then each or this side. So you will have, so therefore you will have n wave functions, which represents these n energy states, and where we will later on fill up these electrons. So we will have, let's say, so if I have n electrons, let's say, or n atoms, so we will have, and each atom, let's say this is a 2s one. So this is, we are taking the example of lithium, so 2s1. So we will have, each atom is providing one electron, so there will be n electrons. So what we were first trying to do is, we try to find out how many energy states we will have, and then according to that we will fill it up with whatever electrons that are available. Okay, and then we will fill it up with those energy levels with the electrons. And how do we get these different and each energy state, which is, let's say, each energy state. So there will be energy states like n energy states, which is given by a energy of En or Ei. So we have a energy, let's say or I look at the picture here. So you have energy here, EB. Okay, so this is one, represents one molecular. So it's not a molecular orbital, it is like a solid now orbital, which is due to the solid, so it is not a molecule anymore. So this is a wave function which represents the all the electrons actually. Okay, so it is not just 2 electrons or 3 electrons, but it represents all the n electrons that you have in the solid. And so it will have a energy EB and a top energy ET, and then in between you will have all the energy levels, all these n energy levels you will have in between. I think we'll continue that since it is time. Yes, so we'll stop and we'll continue this in the next class. Okay, thank you.